Thanks, Malcolm. I never talk behind Malcolm. We're about 10 minutes late, so I'm going to use that. My lecture today, as a matter of fact, is continuation of my last lecture in the COE meetings in, it was, I think, in the Australian Academy in Canberra. And those of you who attended it remember maybe that after half of the lecture, the power went off or so I had no slides to show anymore. So I'll be showing some of this. And just to make sure, you have to show me how to run this. Oh, over there? Oh, okay. Well, doesn't help. Another minute gone. Great, thanks. So just to make sure that I'm not missing this photo, which is the most important one, these are students working throughout the years and some of my collaborators. We've been doing this work for a long time in Okinawa now, about 10 years, in Eilat, and from last year also in Jordan, in Aqaba. And I'd like to mention Professor Sakai from Okinawa, who is my collaborator on this work. This is a summary, as a matter of fact, of all what we know today on reproduction, on sexual reproduction of corals. And it's based on the review by Andrew Baird and co-workers and Harrison, and our recent contribution to the family Fungidae, which the major point there is the fact that many of them are changing sex, and that's what I'd like to talk mainly today. So I will concentrate on gonocores, which are only 25% of the corals that are, we know their reproduction about, and concentrate also on fungiitis, we'll skip that, that is the main coral that I'll be talking about. So my talk outline is reproductive traits of fungiid corals and highlighting sex change in Okinawa, Eilat, and Aqaba Red Sea. I'll talk about reproductive success and aging and possible cues for sex change. So these are the corals that I've been working on in Okinawa, a total of 12, as a matter of fact, that you can see them here. The ones which are in red are the ones that I'm working also in Eilat and Okinawa. The upper one is Herpolita, I'll mention something about him, and the lower one is fungiitis that I'll be mainly concentrated in my talk. So this is a summary of the life history of the corals that we've been working on in Okinawa, 12 in number, and note that all of them, as a matter of fact, are gonocores. Most of them are also spawners. In the GBR, fungiitis has been reported to be a spawner by Betty Willis and Jamie Oliver. And what we are finding in Okinawa, that fungiitis is a brooder. That was a big surprise, as you will see later on. And furthermore, from just 2 months ago, working in Jordan in Aqaba, we expected that fungiitis will be a brooder, but it turned out to be also a spawner. So you may ask if it's the same species. As far as I'm concerned, it's very clearly the same species, but they'll tell me that Favia is not Favia anymore and Stylophora is not Stylophora anymore. So we're going to find that out molecularly for sure. Another surprising result was that there are true sex changes, but protogynous. They start as females, while most of other corals that we've been working on, like the first two that you see here, are protandrous. They start as males and then change into females. Last time we talked about, I reported there were bidirectional sex changes. Now we know that they are multidirectional. In other words, they make it from a male to a female and male at least 3 times that we already know. This is the area in Japan. I'm pretty sure you have seen that. Thousands of fungiids piled one over the other in a very small place, collecting about 12 different species and studying them, then concentrating on only 4 or 5, bringing them to the lab, tagging each one individually, as you can see here, in a number, and following them through time, several years. This is the female of Ctenactis shedding eggs. They're very, very accurate. If you come to Okinawa in July or August, 4 nights or 5 nights after the full moon of July and August, exactly at 10:45, they'll start spawning their eggs. Accurate. Now, the same thing with the males that you can see here, and very easy to distinguish between males and females, but as I said, they're doing it several times, in other words, multiple sex changers. I'm sorry. So here's fungiitis on the reeflet, very easily distinguished. It does not go below 2 or 3 meters depth, lots of them, and very easy to work with. So just to impress you, we've done also the histology. I'm not going to go over it, but we have very detailed information on the histology of these species. So I'll jump that and just want to show you that this is a development from egg to planula larvae and to the young juvenile. So this is unfertilized egg. This is a juvenile planula larvae, immature. This is already a mature larvae infected with zooxanthellae. Cross-section through the planula. You can see here the mesenteries, 6 of them. So we're talking on the halcampoidal stage, just before settlement. And here is after settling, 7 days after settling, a polyp of 6 that you can see there are 6 septa already. Here's the planula larvae. They're very, very tiny, tiny dots. You can't really see them if you don't know what you're going to see. So they are only 270 microns in length, already infected by zooxanthellae. And here was the big surprise that we expected to find the same in Aqaba, but this is just taken 2 months ago. They were all spawners. They spawned eggs. To my disappointment, I really hoped to get their planulae, but that's it. So, okay. Here is a summary of fungiitis after 3 years studying them from 2009 through 13, and the sex change that this particular individual showed. So these are the numbers. Here you can see that change in sex, that all these ones, which are very, very small, only 38 millimeters in diameter, think of about that size, very tiny, they already reproduce and they're producing planulae. Very, very small, and they start as females and change into males. Now, I don't have really a good explanation to that, and if you do, please talk to me. I'd love to hear that. So middle age or size, they're changing from males to females, and bigger ones from females to males. Now, so what we're saying is that fungiitis, at least in Okinawa, is a pathogenous sex changer, starting as female and then goes into male. And this is the detailed data on, of each individual coral, where you can see the numbers. Here, each number is a separate coral, okay? And you can see that these ones change from male to female, and all the rest, surprisingly, from female to male. And there is a reason to that, as you will see in a minute. That is, most of them change from female to male. Again, same population and some statistics of the population. We started with 61 individuals in 2009, very quickly realized that if you want to make population ecology, or study this thing, you have to have much larger numbers or population size. And we increased it to 115. And what happened, that it decreased to 51 because in 2011 was a typhoon that killed 64 of them. They were still kept in the aquaria there. There was lots of fresh water that killed them. It's a long story, heartbreaking. I don't want to go into it. But the end result is, and from every bad thing there is something good. So if in 2010 only 11% changed sex, in 213, 35% of the population changed sex, and all of them from female to male. And my interpretation is that the typhoon caused such a stress to the corals that were there kept in the aquaria, and that was their only chance to survive and increase their fitness. So what we're seeing here, that the very large corals are almost all male. So we're talking on size, on sex size dimorphism, where the larger ones are male and the very small ones are female. Just to wrap up this point, so in fungiitis, we are saying that all of them are gonochoric in all localities. In Aqaba and Eilat, in the Red Sea, they are sequential hermaphrodites or true sex changers and spawners. In the GBR, all that we know is that there are spawners. In Okinawa, that's most of the information is coming. There are protogenous, true sex changers, and brooders. And next question is there senescence in corals, or do corals senesce reproductively? And remember that we are talking on polyps. It's only one polyp. So one way to age them is simply to count the number of growth bands that you can see here. This is done very easily if you turn them upside down. But as they age, their growth rate decreases, so the growth bands are coming very compact. You can't count them anymore. So another way to go around it is to do computerized tomography, which we have been doing, but this also doesn't solve all the problems, because when you get very large ones, again, the growth bands are very dense and you can't count it. So the only really way to do that is what we have been doing, as a matter of fact, all these years, is to study their growth rates of individual growth rates and divide them into size groups. So we have very good correlations now between size, weight, and age. And this graph shows you what I've been talking about, senescence or reproductive senescence. If we count the number of eggs, and in that case it's Ctenactis echinata, versus their weight. For example, here is, each one of these dots is a female. This is an old lady, which is about more than 6.5 kilos. And I can tell you she's now 95 years old. Sometimes I wondered what she's thinking about this crazy Israeli getting her out from the reef after she stayed there for 90 years and bringing her to the lab and back to the reef, back to the lab. So this old lady just gave very few eggs, but as you can see, that reproductive effort is going very steeply up until a certain age or weight, and then decreases, which might infer, of course, senescence. I've showed this that in the past we were trying to study telomeres and expecting to find short telomeres in the old guys or in the old females, and long telomeres in the short ones. So far, I'm sorry to say that we don't have real good data to prove that. All what we can say is that the sperm of Ctenactis exhibits longer telomeres than the somatic tissues, which is quite expected, but this is still going on, and I do hope that we will show that. But in fungia, it's about fungiitis, it's about the same story. So if we count the number of planula versus the diameter, and each one of these is a different specimen, you can see again that fecundity goes up very steeply until a certain age or size, and then it goes down. And it's around 70 millimeters of diameter where you have highest fecundity. And the same story is with the males. If you count the number of spermatozoa per diameter, it's mainly concentrated about 70 millimeters. So clearly there is a size where you get the highest fecundity. If we put both graphs together that you can see here, so 70 is the magic number for fungiitis in terms of highest fecundity. So if we take now the whole population, divide them into different size groups, and divide the population below 70 and above 70, and check what is the sex ratio in the population. So as far as when you look at the entire population, there is no significant difference between males in blue and females in red. And there is also no significant difference in the very smaller ones, that is males are one, females are a bit, it's biased a little bit towards the females, but still non-significant. But there is clear significance with the older sizes, where males are 5 times more than females in the very large size groups. So if you take a very large fungiitis, you have high possibility that it's a male. So again, the conclusion is that reproductive aging occurs most probably due to individual senescence. Again, remember, we're talking on polyps. So it's one polyp which is born, it's growing, it's reproducing, it's senescing, and probably dying. So it's not like other colonies that we treat them as immortal. We do have senescence in these corals. The question then is, why change sex? Why change sex is a lecture of 1 hour, which I'm not going to, and this is the model that may be explaining it. I've showed it a little bit in the past, but as Terry said the other day, models are not explaining things, but rather making predictions. And the predictions out of this model are that sex change is favored when reproductive success or fitness increases more quickly with size or age in one sex than in the other. And the direction of sex change, whether it is from male first to females or females to males, is determined by the relative reproductive success over the course of a lifetime. That's the most important thing to remember for the two sexes. So if you want to study fitness, you have to study them over the course of their lifetime, unless you do it, of course, in different size groups, and that's the way to go. And so what are the possible cues for sex change? We may think of behavior like fish, which is highly unlikely. There might be chemical cues like hormones, or there may be a situation where there are energetic or environmental constraints, different constraints that you can see here. We've been testing a bit out of that, which I'm not going into detail, but tying large male to small females and expecting a year later to get this large male to change into a large female and the small female to a small male. I'll let you think out why it is a direct result out of the model. This is what we've been doing in Okinawa, tying them together and marrying them for at least a year. As a matter of fact, they're married already there for 2.5 years. I had no chance to see them, unfortunately. But the expectation is right there. And we've been doing the same thing with Herpolita now, just 2 months ago in Jordan, in Aqaba, doing the same exercise with Herpolita. By the way, Herpolita, by chance, we found out that it's a day spawner. Both fungiitis and Herpolita are day spawners. Fungiitis starts with sunrise. Herpolita, exactly 9:45 during daytime, starts spawning. So for 6 years, we were looking at nighttime in Okinawa. We didn't find anything until I asked 2 students to look at my things. They overslept at night. They came at 9 o'clock in the morning, and then they found it out. So that's pure luck, and that's how we know this story. So Another way to cause them change sex is by disturbance. If you cut them into two, split them, and I did that with females, so I can tell you that within a year you can see the regeneration that is taking place. This is 12 months after breakage. Half of the population did not reproduce. Half of them turned into males as expected. I would expect that after 2 or 3 years, they will go normal and change into females. So I'd like to end up with this lovely quote by Darwin from his book on the descent of man, 1874. And this is the second edition of his book. And quote, he says, "I formerly thought," that is in the first edition, "that when a tendency to produce the two sexes in equal numbers was advantageous to the species, and that would follow from natural selection. Now I see that the whole problem is so intricate that it is safer to leave its solution to the future." I'm afraid that we are still at the stage where we have to leave the solution to the future. And I'll let you find out, to draw yourselves the conclusions, and thank you very much.